As you can see, we have new blackboards. I think we can thank Wolfgang Rudolph and Gary Harrison and Steve Portillo for the blackboards. Did that movement of the hand, was that a question?
It was, just in passing.
What?
Why did they
What? What's the question? Do you like one?
No, thank you.
What's the question?
Why did they install whiteboards?
Why did they what?
There are whiteboards in the room.
Well, there are whiteboards. I don't like
Why
whiteboards.
did they replace these with whiteboards?
Why don't we?
Yeah.
All right, what I've found in the med school, where they have more money than here, they have nothing but whiteboards. Okay. I have never seen a whiteboard with a pen on its chalkboard such that you could take the pen and write on the whiteboard. I've never seen it. Whenever you pick up the pen, it's dry.
You mean you don't carry them with you?
Well, come on. I mean, I think whiteboards are a disaster. And also, I once had a whiteboard actually in Shanghai. And so the first thing I did was try to erase what was on it. Couldn't, impossible to erase.
Well, that was months ago.
Huh?
That probably was several months ago, you know.
It was too long ago?
Yeah, in that office, I know.
Okay, well, he knows the board I'm talking about. I went to the shop at the store at Shanghai, and I got pure alcohol, and I tried to erase. I think I eventually got it off, but I mean, it was just totally laborious. It's just awful. And then I couldn't find a pen that I could write sensibly on it. I mean, it was just a complete disaster. So that's the answer to your question.
There we go.
My answer to your question, I mean, it may be that in some places this works. All right, what I'm going to try to do is finish plot 1 finally. But, and if we have some time, I'm going to try to review the LSZ and the vacuum and the time ordering and all that. Now, I'm not sure which chalk to use now that we have nice blackboards. So let me review first of all what we were doing last time. We had basically, well, first of all, we know that FSI is a product of things like this, minus I integral. In this case, where we had just one particle in, one particle out, it was p forth x1, e to the minus I, p1 x1, p1 squared. That's p initial, so this is p initial. And then it was minus I integral p forth, well, this is x, I don't know, it's kind of x1 p initial, x2 e to the I p final, x2 p final squared. Okay, so it's a kind of a hybrid notation. And then physical vacuum, time ordered product, phi x1, phi x2. Okay. And literally, everything here you can think of as Heisenberg. In other words, Heisenberg vacuum doesn't move, fields move, but with full interaction time dependence. But we can rewrite that in terms of the interaction picture. And so in particular, we were looking at one particular case which we call T1. So this is minus bracket T1. And that turned out to be minus integral p forth x1, p fourth x2. Is this visible in the video?
Yes.
Okay. E to the minus I pi x1 p initial squared e to the I pf. Remember, it's plus here, plus for final, minus for initial, but always minus I. Pf x2 oh, I see now I was on the wrong line with my eyes. So let me it's actually P1 minus Pi here times x1, and here it's Pf minus P2 times x2, and there's a factor of minus g squared over 2, and then this was rather a long formula, d4 p1, d4 p2, d4 k over 2 pi to the 12th I over, we took the massless case for simplicity, I over p1 squared, and I'm leaving out the I epsilons, I over p2 squared, I over p1 minus k squared, and I over k squared. And actually, in this particular diagram, the I epsilons, I shouldn't have really dropped them, and I don't really mean to drop them, but we just don't have space. And if you imagine this is all one formula, then it's 2 pi to the 4th, delta 4, p1 minus p2. So that's what we've got. And now if we do some of those integrals and use the delta function, we get g squared over 2 integral pi squared pf squared delta 4th. Well, the x1, x2 integrals, of course, give us the delta of p1 minus pi, p2 minus pf. And this is then delta p1 minus pi, delta 4th of p2 minus pf, or the opposite. And then a 2 pi to the 8th. And then all that other stuff, which is, why don't I just, I mean, it seems crazy to write all this again, so I'll just put on the ditto where this means everything from here to there. And what happens? Well, this means that pi gets set equal to p1, pf, or p2 gets set to pf, p1 gets set to pi, and so those terms cancel. Actually, now that I think about it, in as much as I want them to cancel, it might be good to actually write this. So it's d4th p1, d4th p2, d4th k, 2 pi to the 12th, and then we have p1 squared, p2 squared, p1 minus k squared, delta 4th of p1 minus p2, and I'll just put I to the 4th there, and a 2 pi to the 4th. Okay, so this is what it looks like. Now these delta functions mean that these guys become p1 squared, p2 squared, and they exactly cancel here. And so what we wind up with is minus g squared over 2 integral d4th k 2 pi to the 4th I over p pi minus k squared. That's because p1 is set equal to pi. And then I'm going to put in the plus I epsilon I over k squared plus I epsilon 2 pi to the fourth delta fourth of pi minus pi. Okay. And what's happened then is that the external legs have canceled. These external legs are the 1 over p1 squared and 1 over p2 squared. These are the propagators for the particles coming in. And this, we're to interpret the S matrix then as 1 plus 2 pi to the fourth delta fourth of the sum of all the incoming and outgoing momenta, and then Im. So Im is this thing here. And in other words, Im is minus g squared over 2 integrals d fourth k. If you cancel these two pi's, this is what we've got, and then an I over pi minus k squared plus I epsilon, I over k squared plus I epsilon, and okay, so that's actually it. Now this is an example of Feynman's rules. Feynman's rules in momentum space are, and again, this is for a scalar field theory. 1, internal lines give I, with momentum p, give I over p squared minus m squared plus I epsilon. So that's just the Feynman propagator, which is the mean value in the free vacuum of the time-ordered product of two free fields. 2, vertices from Li give typically something like Ig if G is the coupling. Notice I restrain myself from saying constant because couplings actually in perturbation theory change with the scale. External lines, no propagators. Propagator is this thing. 4, some p equals 0 at every vertex. 5, oh, might as well go over here. 5, integrate over internal momenta. And 6, some overall diagrams. Well, there are an infinite number of diagrams, so you can forget that last step for practical purposes. Although there has been one of the things about string theory is that people have found some remarkable ways of summing Feynman diagrams in some cases and in some theories. And I'm not really familiar with that work, but this sum all diagrams, it's I don't think it'll ever be possible, but on the other hand, there has been progress in the last actually it's not the last, it's not just the last few years, it might be the last 40 years. Okay.
Are you saying that no one has developed a graphical calculus for Feynman diagrams?
Sorry, what was the beginning of the sentence?
So have people been working on sort of a graphical calculus for Feynman diagrams?
I
You could put them together and make them right? Reduce them to something a little more simpler and calculable,
Like you do what?
to make them simpler.
As I said, I'm not familiar with the work. I think it has something, it's strange. It seems to have something to do with Spence functions and funny identities having to do with certain special functions that, you know, normally we never look at or think about. Again, I'm just saying, the only reliable thing I can say is that there's been progress. I don't know what it is, so, sorry. Okay, let me now do some more topics, and then, as I said, if we have time, I want to go over the LSE, the vacuum, the various pictures and so forth. And I think it's simpler than, well, I think you need to see it again. Okay. External momenta, of course, have their physical on-shell values. On-shell means p squared is m squared, or the energy is the square root of the 3 momentum squared plus the mass squared. And there's an overall factor in these scattering amplitudes, of course, of the delta function of the sum of all the 4 momenta in is equal to the sum of all the 4 momenta out. For internal lines, in as much as the momentum carried by the internal line is squared, we don't really care whether it's whether we keep track of the direction of the momentum. But when you're doing it, it's better to keep track of the direction. It's better to decide how the momentum is going, and because then you can easily conserve it at each vertex, and you can keep track of things. And in fact, you'll see when we do fermions that we'll have a p mu gamma mu up here, so we need to keep track of the sign of the momentum, so we might as well do it even when we don't need to do it. Pictorially, we can think of it like this: P1, P2, then this line is P1 plus P2, and then P3, P4. Okay. Sometimes, in fact, Weinberg's choice is to have time going up, and so you take this whole thing and rotate it. And of course, at each vertex, the momenta are, the 4 momenta are conserved. Now, there's a matter of disconnected diagrams, and an example of that is that Schwartz gives is, suppose there's a muon coming along, and it decays into an electron and an anti-electron neutrino. This is a W going across, and this is then final state electron, so it looks like this. And we can put a momentum on this. By the way, the reason why these guys are funny is that conventionally you write antiparticles with the arrow going the opposite way of the physical momentum. We'll see that later. So suppose we have this 2 diagrams here. The other one looks just about the same. In fact, it is the same, except maybe the momenta are different. Well, we can imagine that this is a 2 to 6 process, 2 muons in and 6 fermions out, but it's a disconnected diagram. And if we computed this with Feynman diagrams, this thing would be the product of 1 3 times another 3. So it would be the product of the 2 Feynman diagrams, the 2 Feynman amplitudes. Now that's to be distinguished from a connected diagram, which might look like this. Maybe a Z goes across, and the mu comes in, and So I'm just doing, so here is a connected 2 to 6. But now this thing would look like that. The delta function properties of these are quite different. This one would have an overall delta function of times, you know, I am 2 pi to the 4th and so forth. This one, on the other hand, would be I squared 2 pi to the 8th and I am prime, where this is, and delta 4th of sum to 3 minus P1, whatever the initial muon was, delta 4th, sum up to 3 of the final momenta, prime, say, double prime maybe, minus P2. So this thing would have 2 delta functions, this would have 1 delta function. And that's basically characteristic of these, of disconnected diagrams. And these matrix elements M, which are integrals over, you know, they're just given by this recipe here, integrals over d4 p, integrals over all the internal momenta, and then the phase factors, such as these, and then the phase factors that come from the fields themselves and so forth, so that Feynman propagators and so on. These never make delta functions. I mean, they might have a discontinuity somewhere, but they never create delta functions. And there's a deep consequence or let me start over. Obviously, if you do an experiment here and you do another experiment in Chicago, they normally should not interfere with each other unless you have a you have a beam of neutrinos and actually aim it at Chicago. But in general, experiments that are carried out in different places are independent or have uncorrelated results. And Weinberg says this is absolutely necessary to have any kind of a physical theory, because otherwise, in order to interpret the results of any experiment, you'd need to know what was happening everywhere in the universe. And it's just, you know, absurd. And what Weinberg points out in chapter 4 of volume 1, and what Schwartz alludes to, is that the notion of connected diagrams and disconnected diagrams and delta functions can be understood to imply or to explain why in quantum field theory the distant experiments or the results of distant experiments are uncorrelated. And of course what I mean is disconnected experiments, the example where you go to Los Alamos and you take the lamp proton beam and you aim the neutrinos at Fermilab, well then you would have a connected diagram in principle, because the neutrino would come out of Los Alamos and enter into a detector in Fermilab. All right. This concept that distant experiments yield uncorrelated results is called cluster decomposition. And it turns out that it's a consequence of doing field theory the way we're doing it. In other words, the way we're doing field theory is we say the fields are linear combination creation and annihilation operators. These creation and annihilation operators have we can give them free field time dependence, just as long as we include the interaction of the interaction part of the action density, L sub int in Schwartz's language, and everything's written in terms of fields, and the fields are linear combination, creation, annihilation operators. They all have phase factors. Those phase factors give you these delta functions and so forth. And in fact, Weinberg points out that the reason why people in condensed matter use creation and annihilation operators when they do non-relativistic field theory, even though the number of particles may be fixed in some theory that they're working on, is that they want to have cluster decomposition. Okay, so cluster decomposition in symbols means, and let me use Weinberg's notation of alpha and beta. Alpha for a bunch of labels for the incoming momenta, spins, types, and beta for the to label collectively the outgoing momenta, spins, and types, although we're talking about spinless particles of one field and it's just momenta. So what we would say here is S beta alpha, or rather S beta 1 dot 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 beta n, alpha 1 dot 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 alpha n, where, all right, let me just say what this is. This goes to S of beta 1 alpha 1, S beta 2 alpha 2 dot 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 S beta n alpha n, if the alpha 1 beta 1 are the variables for one experiment in one physical location, alpha 2 beta 2 are the variables, the momenta say, for another experiment done in a totally remote place, and so you have maybe n different experiments all widely separated in space, and let us say at the same time, so that there's no question of one shooting the particles into another. So this is, as you separate the experiments, the S matrix factorizes. And once the thing factorizes, well, then the results are uncorrelated, because the probability are just products. So factorize. Factorizes. I always hesitate when I write clearly on the board because spelling is not my strong suit. Okay, let me define, we have a notion of what connected means, and of course from the point of view of a Feynman diagram, connected means that you can't separate the diagram, or you can't cut the thing in two without crossing some line, okay? So here, these are disconnected, so you can separate them by, you can draw a line through the diagram and not intersect any other line. Here you can't do that. And so that's connected. Now there's Weinberg gives a very nice definition of connected. He says the S matrix is we can define it in this way. You sum over all partitions of the variables alpha and beta into sets. So here I had alpha 1, beta 1, because they were the variables for a particular experiment in one location, and alpha 2, beta 2, the variables for another experiment in a distant location. So here, imagine that you do all sorts of assortments of the alpha and beta into different sets. And this is the connected S matrix for this beta I, alpha I, dot, 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 SC, beta J, alpha J, and so forth. In other words, that's a definition of connected. And you can see that this makes sense. For example, you would say that S11, well, this is just proportional to the delta function of P1 minus P1 prime minus P1. So at the lowest order, this thing is completely trivial. On the other hand, if you have S22, Well, this is going to be SC 22 plus the disconnected diagrams. Well, the disconnected diagrams in this case, in other words, this one would look like this. The two particles come in, there's some kind of an interaction, and they go out. And then, these are the other ones, okay? And these are delta 1 prime 1, delta 2 prime 2, or, so 1 prime 2, 2 prime, or 1, 2 prime, 2, 1 prime. Well, all right, and so forth. Might be other permutations. The same thing with 3,3. S33 would be the connected 3,3 plus a delta times connected 2,2 plus various permutations plus delta, 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 meaning you have. And so in other words, it's this thing is equal to connected 3 to 3 plus 2, 2 like this, plus and so forth. All right. So what we can see then is that the S matrix essentially will factorize in this way as long as the connected part of the S matrix vanishes when the S matrix represents two independent experiments. Okay. Because in other words, well here the best way to do it would be to do S44 again. S44 then is going to be connected S44 plus, for example, 2, 2 plus dot, dot, dot. I'm leaving out some others, but the point is then that this is the connected at 4 to 4 plus disconnected 2, 2 by 2, 2 to 2 disconnected. And now if this one factorizes when the some of the momenta, or if this goes to 0 when some of the momenta are distant, then if this represents an experiment here and this one an experiment far elsewhere, this S matrix will factorize, it will equal this if this one is 0. And so what we want is that the connected S matrix should vanish when it represents uncorrelated or distant experiments. Sort of the FedEx theorem, I guess. Or the UPS, also known as oops. That was called oops last Christmas because they were late with a lot of deliveries. People get upset when deliveries are late at Christmas. All right, let me show you now why it is that this connected S matrix does go to 0. And let me just remind you what it looks like. It looks like this. Let's do it in position space. Then it's d cubed p prime, d cubed p. Some connected, I'm doing the Fourier transform in other words. The connected in position space is the connected in momentum space. And then it would be e to the I p prime x prime minus I px. Okay. And what is this connected S matrix? Well, it has an overall delta function. So this is d cubed p prime, d cubed p. And this would be a delta for all the p primes minus the p's. Well, I'm writing it a product sum sum, and then, and what's left is some sort of a smooth function of p prime and p. And then, of course, this Fourier transform type factor, UDI p prime x prime minus px, and I'm thinking that we sum over them all there. And the point is that this guy is more or less smooth. It might have a discontinuity, but nothing worse than this. And now, it's hard to see, it might be hard to see why it is that this goes to 0 if it's describing two experiments that are widely separated in space. But we can see it if we just go down to the simplest level of just two variables. So in other words, we have just dp prime delta p minus p prime e to the I px minus I p prime, let us say y, and then some c of p and p prime. Well, the delta function tells us that we can integrate over p prime as long as we set it equal to p. So this is then integral dp e to the I p x minus y, something smooth, c of pp. Okay. All right. Well, there's I forget which people gave this theorem first, but if this is some sort of a smooth square interval function, then as we let x and y differ enormously, this thing goes to 0. So this goes to 0 as x minus y goes to infinity, as long as this function here is not totally nuts. Okay. And for example, if this were Gaussian in p minus p squared, then this thing would be a Gaussian in x minus y squared. Gaussian in x minus y. And similarly, for anything reasonable here, goes to 0 as. So that's basically why it happens, and these phase factors themselves come because we have fields that have the A and A dagger, and they contribute these phase factors. Okay, the bottom line then is, if we're doing perturbative scattering theory, which is the main subject of Schwartz's book, then all we have to do is think about things like this. Free fields, free vacuum, connected. And in particular, if we say connected, then all the bubbles are gone also. So the bubbles in the disconnected diagrams, forget about them, they're gone. Bubble means a diagram that has no external line. Okay, that's a bubble. Disconnected, we know what disconnected means. So we forget about all that and we just do these. Now, bubbles are related to the vacuum energy because in fact what we saw was that the bubbles were essentially came from vacuum. Well, they came from something like this: 0 e to the I integral d fourth x L interaction 0, and so that you see is something associated with, somehow related to the vacuum energy. But normally we don't think much about the vacuum energy because our renormalizable field theories are so wildly divergent that the possibility of computing the vacuum energy is pretty much hopeless. All right, now I want to do some examples. And these are simple examples of Feynman diagrams in the simplest field theory. This is highly unphysical, this field theory, because it's not Hamiltonian, it's unbounded below. But anyway, here's the action. Schwartz likes to integrate by parts for some reason. I think because it's what?
Lay and I
So can you
were having a
explain
discussion about
What?
Lay and I were having a discussion about why this term represents kinetic energy.
Oh, he's integrated by parts. What he should write here is minus a half d mu p d mu p. That's the standard way of doing it. If you LaTeX this, you have to, you either, I mean, if you actually just use the standard macros that are built into LaTeX, this is, 20 keystrokes to do this. It's maybe 4 to do that. You just write \capital DOX, I think is what it
It
is.
is, absolutely.
Yeah. Whereas here it's \partial submu, and then he has to do supermu, or he puts them both down, which is
You
kind
could
of
just
dumb.
write your own command.
Well, that's right, \p is partial for me.
There we go.
Yeah. So I write this, I don't like it. You want a candy?
Nothing.
Okay, so the rest of this is -1/2 m squared pi squared, and then plus g, whoops, g 3 factorial pi cubed. By the way, there were typos in the homework assignment that the solution to the homework assignment, there were typos in the version I sent you last week, so I sent you a new version yesterday or the day before. All right. In 5.32, we saw that d sigma d omega 2 to 2 is 1/64 pi squared e squared center of momentum, or p equals 0 frame. I don't know. 0 momentum frame. That's what I'm going to call it. Times the amplitude squared. All right. Now we're going to use Feynman's rules to compute m. What do we get? Well, we get Im is, first of all, it's this one. P1 coming in, P2 going in. Well, momentum's conserved, so this has got to be P1 plus P2, P3 out, P4 out. So what is this? Well, here's a vertex. We get IG. Here's a Feynman propagator, we get I over P1 plus P2 squared minus m squared plus I epsilon. It turns out the I epsilon can be ignored in tree diagrams. Tree diagram is one that looks like a tree, especially if you turn it about 90 degrees. These are the roots and these are the branches. Mandelstam introduced a notation where this thing here is called S. So, oh, there's another vertex, IG. Okay. So this thing is minus IG squared over S minus M squared. And as I said, you can ignore the I epsilon in the tree diagram. Where S is this thing here, P1 plus P2 squared. So this we might as well call MS for the process that P1, P2 gives you this, and so forth. All right. This is a T diagram, and this one is P1, P2, P1 minus P3, because P3 is going off there. And then this is P4. This thing is IG for one vertex. I over P1 minus P3 squared minus m squared plus I epsilon. IG for the other vertex. And now Mandelstam called this T. Minus IG squared T minus m squared plus I epsilon. And there's one more. IMU, and this is, well, we can say, put it this way. P1 comes in. Now there's a vertex, and P4 comes out like this. And then P2 comes in. And that's P3. All right. So now, what is this? Well, it's again IG. I over, and what's this momentum? Well, it's P1 minus P4. So it's I over P1 minus P4 squared minus M squared plus, well, forget the I, and then IG. So it's minus IG squared U minus M squared. Okay. These things are called Mandelstam variables. Now the actual cross-section is then d sigma d omega is then g squared squared, so that's g to the 4, 64 pi squared e center mass squared, and now 1 over s minus m squared plus 1 over t minus m squared plus 1 over u minus m squared squared. So this is, of course, a very nice notation. And ST and U are obviously Lorentz invariant because they're squares of four momentum. And so you compute in your zero momentum frame, and then you've got it in every frame. The Mandelstam variables also satisfy a very simple identity. The sum of S plus T plus U is the sum of all the masses. And I can show you that briefly. I'm trying to save Blackboard space, but I guess I'll just do this. S plus T plus U, well, this is, of course, P1 plus P2 squared plus P1 minus P3 squared plus P1 minus P4 squared. By the way, in this particular process, S is positive, T and U are both negative. Okay, what is this? Well, this is obviously P1 squared plus P2 squared plus P1 squared plus P3 squared plus P1 squared plus P4 squared, and then other than the cross terms. Each of the Pi squared is just M squared. So this is 3M1 squared plus M2 squared plus M3 squared plus M4 squared, and then plus 2P1, P2 minus P3 minus P4. But P2 minus P3 minus P4 is minus P1. So this is minus 2M squared. And so altogether this is equal to M1 squared plus M2 squared plus M3 squared plus M4 squared. So the Mandelstam variables not only Lorentz invariant, but they have this cute mass relation. And I don't know what this is. It must be have been some protective something or other that go away with use, I hope. Any questions? Yes.
So according to that rule 4, you would have the at each vertex you would have the 4 momenta conserved, right?
At each vertex you have 4 momenta conserved, and the total 4 momenta are conserved.
But in this case, in the first diagram, if the line connecting the two,
This line carries P1 plus P2.
what if the mass of that is 0?
You're asking a marvelous question. The internal lines are always off shell. In other words, this thing, P1 plus P2 squared, or S squared, is not the physical mass of, well, there isn't any 1-2 particle to begin with. And secondly, it's not certainly not the mass, suppose this is just one field, so there's just one mass in the theory. P1 squared is m squared, P2 squared is m squared, P3 squared is m squared, P4 squared is m squared, P1 plus P2 squared is not m squared, something else.
Okay.
All right?
Okay.
In fact, it's 2m squared minus 2p1 dot p2. Whatever that is. Okay, good question, and that actually now realize I owe you 2 candies. I don't know if you're that hungry, but you can put them in your candy store. Any other questions? All right, let me tell you a very brief Mandelstam story. He was once giving a lecture at Berkeley years ago, before most of you were born.
What?
And the first thing he did was he looked for chalk, and he couldn't find any chalk except this tiny piece. And this was during the Reagan era. And one of the things Governor Reagan did as governor of California was to reduce taxes and screw the universities. And of course, he could be excused to some extent because there was a referendum that, I forget what it was called, but to put an upper limit on property taxes. You couldn't raise property taxes again. And so Mandelstam looked around, just found this little bit of chalk, and he said, just how bad is the budgetary situation here in UC Berkeley? Well, everybody laughed. I thought it was funny. I guess I don't tell stories as well as I should. Let's get some more lighting in there. Okay, just how big?
They also have these really thick pieces of chalk.
Yeah, I don't need to use the big chalk because we have good blackboards now. Let me get a fresh piece of ordinary chalk. All right, so that was an example of what I've done. Now let me just say something to you that I think is important. You could just take this as L int, and you could just put it inside time-ordered product e to the I integral d4 x L int, and so it would be g cubed over 3 factor g. You have g over 3 factorial phi cubed, and this would be a free field. And you then have P1, P2 here, P3, P4 there, and you'd have that time-ordered product. First term is 1, but it gives 0 because the momenta are, say, all different. The term that's linear in phi cubed, 0 also, so you've got a term with 2 phi cubes, which is the thing that we were looking at last time. Although we weren't looking at it for a nice process like this, we were doing it with those crazy bubble loads and so forth. But we were focusing on the stuff that Schwartz has now told us we should ignore. Disconnect bubble diagrams. Anyway, what you can see here then is if you have phi cubed and phi cubed, when you have two of these fields, produce annihilation operators that annihilate these two guys. Two of these fields produce creation operators that create these guys. And then you've got one left over, and that gives you the propagator, since you take the time-ordered product of it. And of course, you've got 3 factorial ways of taking the annihilation operators from either this group or that group and annihilating these, because P1 can choose to couple with phi 1, phi 2, or phi 3 here, and so that's 3 factorial. And Okay, so in other words, you can do the thing by hand, and you wind up with the result that we just got. And it might be useful for you to do that. In fact, that's what actually Weinberg does when he teaches the Feynman rules in his book. It's chapter 6. He actually goes through, he considers 3 different theories, and he goes through the, well, obviously in Weinberg he skips steps, but he basically goes through from the very beginning to the final answer. And so that might be something that you want to do. Instead, what we're going to do now is consider a theory with derivative couplings and again use the Feynman diagram technique. So now we're going to think about Li as being lambda phi1 d mu phi2. Where that water came from? Well, I erased the board before class, but I don't know, I think there's a non-polar coating on the blackboard that will come off with use, I hope. Okay, well, you remember what a free field looks like. The derivative of the free field, for example, d mu phi2, this is integral d cubed p 2 pi cubed square root of 2 omega p, and then minus I p mu ap e to the minus I px is the full momentum, the Lorentzian product, ap dagger e I px, like that, okay? So you get, so for every incoming particle, you're going to get a minus I p mu. For every outgoing particle of momentum p, you're going to get an I p mu. And of course, it's going to be Lorentz contracted in this way, so momentum 2 will be contracted with momentum 3. Okay, so let's compute a particular diagram. Phi1, and now you see he has to say that it's field Phi1 so that we know what the derivative structure is. Phi2, P2, P1. By the way, people often write dotted or wavy lines for the intermediate, for the internal lines. I don't know, you can do whatever you want. Phi1, but now this is P1 prime, and Phi2, P2 prime. So this is when field 3 is kind of a spectator field, and particles of type 1 and 2 come in, particles of type 1 and 2 go out, and we're going to look at this particular diagram. Okay, so this is equal to Im, which is equal to, well, we have 2 vertices, lambda, so we get I lambda squared. We then have a P2 coming in, so we get minus I P2. And I'll put a sub mu on it. And then we have, this one has to be 3, and it's momentum P1 plus P2, and it's coming out of that vertex, so it's I P1 plus P2 mu. So in other words, all we've done here is, I mean, most of this is just that one vertex. And then the propagator is going to be I over P1 plus P2 squared minus M3 squared. And we don't need the I epsilon here. And then, notice we know this is a 3 because if we have a vertex and we have a phi1 coming in and a phi2 coming in, well, we don't have any other operators over here except the phi3 kind. Now the other vertex has a P1 coming out and a P2 coming out, so the P2 is going to give an I P2 mu. But it has a P3 coming in, so that's a minus I there. So this thing is going to be minus I P1 plus P2, and now we can call this nu if we want. And then the other one is I P2 prime lower nu. In any case, it's contracted with whatever the other one is. Okay, so this is the Feynman diagram, and it's a little bit late. Let me just say that either you follow Schwartz or you trust me. This turns out to be minus I lambda squared P1 dot P2 plus m squared, and I mean four momenta here. P1 prime, P2 prime, plus M2 squared, and then the denominator P1 plus P2 squared minus M3 squared. All right, so that's the the amplitude. And Schwartz points out that if we change the Lagrangian by, the interaction Lagrangian by an integration by parts, and we go to Li equals minus lambda phi 3 d mu phi 1 d mu phi 2 minus lambda phi 1 box phi 2 phi 3, and we use this theory to compute the same amplitude, we get the same answer. So he's just verifying that total derivatives don't affect things. And one reason why they don't, another way of looking at it is if we say Li is d mu of some v, in the sense of, I don't want to, I shouldn't have written that. Let me write it this way. D mu of, say, phi 1, phi 2, phi n. Now, obviously, this is a nutty interaction with Lagrangian because it's not Lorentz invariant. Okay, but he just wants to illustrate that derivatives aren't going to affect things. And the point here is that you see when you compute this, what is it going to be? Well, it's going to be d mu phi 1 phi 2 phi n plus phi 1 d mu phi 2 phi 3 phi n and so forth. There'll be n terms there. And when you compute it, this is going to give a derivative, this is going to give a momentum, that's going to give a momentum. And some of them are going to be incoming, some of them are going to be outgoing. And the whole thing is going to be the form sum p in minus p out, or minus sum p out, times sum v for vertex. This thing vanishes, so the whole thing is zero. So the contribution then of derivative terms is zero to scattering processes, at least in perturbation theory. Another way of thinking of it is if you add a total derivative to an action, you for sure can turn it into a surface term, and if it's just a surface term at infinity, it can't affect the local equations of motion. That's another way of thinking about it. On the other hand, there are sometimes some things that do matter. For example, there's a term, a famous term, mu nu alpha beta, f mu nu, and I'll make it non-abelian. So A sums over colors or something. This thing is a total derivative. In fact, it's 4 d mu of epsilon mu nu alpha beta A alpha d beta A nu A. Okay. So it's a total derivative. So it's not going to affect equations of motion or perturbation theory. On the other hand, it may affect the electric dipole muon and the mass of the eta. These are the eta prime. The effect on the dipole moment of the neutron is puzzling because experiments have shown that the dipole moment of a neutron is below whatever the best experiment is. And these are actually very, very important experiments, because in supersymmetry and other theories beyond the standard model theories, you typically get a huge electric dipole moment of the neutron. And so all sorts of supersymmetric theories have been ruled out by these experiments. The eta prime, I don't know, I haven't thought about that for a long time, so I'm not going to tell you much about that. All right, I'm going to stop here for this part of the lecture, and instead now try to tell you a little more about the vacuum and LSD and so forth. So I've got, oh Christ, I've only got 7 minutes. And I have to erase the board. Well, some of it's there, and some of it's welcome. So. In fact, let's remember that what we've got is basically physical vacuum on both ends, time-ordered product of the fields, and we can think of them as Heisenberg fields. All right, so let me just say what's going on here. This is a repeat of what I said before, but I think maybe it's good to see it twice. All right, the Heisenberg fields go this way. Time 0. On the other hand, at time 0, the Heisenberg field and the free field are the same, because, or at least we think of them as the same. And so I can say this is e to the I ht phi 0 x 0 e to the minus I ht. And on the other hand, the free field we know at arbitrary times is e to the I h0t phi of x0 e to the minus I h0t. It follows then that phi 0 of x and 0 is e to the minus I h0t phi 0 xt e to the I h0t. Now if you take this thing and stick it in there, you see that this is equal to e to the I ht e to the minus I h0t phi 0 of x and t e to the I h0t e to the minus I ht. All right, so this is the basic relation that was used to go from Heisenberg field to free field. This is the free field, and this is what you can think of as u of t and 0. So this is something that we computed last time. Let me now say what the vacuum is, and I'm going to think of it this way. The physical vacuum, so here's what we're thinking, that vacuum is equal to that in some sense, so to speak, at t equals 0. But I don't know if that's a good way of saying that. Maybe I actually shouldn't have said that. Let me tell you how I think of it. Let's put omega to be e to the minus I big T 1 minus I epsilon h e to the I t h0 on the bare vacuum. Okay. Why does this make sense? First of all, the minus I times minus I gives you minus 1 times epsilon times h times big T. So this is basically going to suppress any of the high energy states. Okay. So in other words, the vacuum of the free theory is the vacuum of, is a linear combination of various states, the vacuum of the interacting theory, and then all sorts of other stuff. The other stuff, which is of higher energy, gets suppressed if you do this. And in fact, I think this is the best way of thinking of where the I epsilon comes from. Not in Feynman's propagator, because that's automatic, but why it occurs in the path integral. But more of that perhaps next semester, or much later at least. Okay, so well, we're going to be really out of time, aren't we? We've seen that this thing which I like to set t0 equal to 0 because I think it's just silly to have t0. We saw that this was time-ordered product e to the minus I integral 0 to t v in the I means interaction picture. In other words, free field, let me call that V0. In other words, it's the interaction potential, or the interaction energy, potential energy typically, with free field time dependence. And that free field time dependence means this. Okay, now, on the other hand, and of course this thing is also what we were speaking of, let me make sure I get it right. This thing is also e to the I h0t, e to the minus I ht. We worked that out before. Now we can define something else. R of 0t, e to the I ht, e to the minus I h0t. Turns out it's good to look at this separately, I think. And now, if you differentiate that and think about it, what is it? It's not time ordered, it's anti-time ordered. So I'm turning the time ordering symbol upside down.
Is that a standard convention?
No. I've never seen it before this afternoon. And what's left is e to the I integral 0 to t, v0 of t prime dt prime. So this is a backward integral. Now look what's q. U of, let us say, t1, 0, r of 0, t2. What is that? Well, that will be, let me do a big equal sign then. That'll be forward time ordering e to the minus I integral 0 to t, v0 of t prime dt prime. And then backward time ordering, e to the I integral 0 to t2, v0 of t prime dt prime. Now, what does that mean, backward time ordering? Let's suppose t1 and t2 are both positive, because the human brain doesn't deal well with negative numbers, at least this human brain. So what does this mean? This is anti-time ordered, so the 0 is on the left. And it comes in plus. Here, 0 is on the right, comes in minus. So what do? It's like Pac-Man. This guy, chop, chop, chop. And this one, chop, chop, chop's the end of this thing. Until what? Until it's gotten to T2. And then there's no more chop, chop. So this is actually equal to the time order e to the minus I integral t2 to t1, v0 of t prime dt prime. So that's what that is. All right, so keep this in mind, and, what is today, Wednesday? All right. Monday, I don't know how you can remember it on Monday. So maybe I'll review this on Monday, finish the whole story, and, I hope I think this will make things, I think it'd be good for you. All right, any questions? It's possible to just, ask me, what's my name, and I'll give you a candy, whatever you want. All right.